Hi, my name is Saif Rayan, and I'm a postdoc in Professor Pritchard's group. Professor Pritchard cannot make it to this office hour.
So the first problem that we have is a car is stopped at an intersection with a red light and a biker in a bike lane, with velocity v is approaching the car. When the biker is a distance d from the intersection, the light turns green, and the car begins to accelerate at a constant acceleration a. If biker just barely catches up to the car as the car accelerates, how far from the intersection will the biker just catch up to the car? And we're only supposed to use the variable d in our answer. Maybe we should write down some equations and try to make it work.
Well, what is this? What equations are we going to use? What is this talking about? So the biker just catches up to the car. So what's physically happening?
He catches up and then falls behind again, maybe?
Oh yeah, that makes sense. Because if he was going so fast, like, he would overtake the car, and then the car would overtake him. But if he just catches up,
Or he wouldn't catch up the car at all.
So yeah, you guys, you're basically talking about, in this problem, you have two different systems. You have the bike and you have the car. And each one of them has a different type of motion, right? So
yeah.
The car has motion with constant acceleration, while the bike has motion with constant velocity. So what you want to do is that you want to figure out how the two motions are relating to each other. This is what you're trying to figure out right now.
That's true, and it's nice and simple that the car is just accelerating and the biker is just having constant velocity. So this makes me think of graphs.
Maybe we should draw some.
Yeah, let's do it. So, actually, I'm going to move this over here. This is what we want at the end. Okay. So, how about acceleration graphs? Since that must be really easy.
Yeah, straight horizontal lines. Nothing too crazy about that.
So, the car has an acceleration a, right?
Mm-hmm.
And then the biker has an acceleration 0. Yay. So moving on to velocity.
Velocity, the car should be a diagonal line, right?
Why is that?
So this constant acceleration, that means the velocity is going to increase at a constant rate, since the rate is changing is acceleration.
All right, so it's going to be a constant slope upwards.
Yeah.
Because acceleration is constant. Okay, and the car starts from rest.
Mm-hmm.
Starts from 0, and draw this corner here. Okay.
And the bike, that should just be a horizontal line.
Because we're in velocity and constant velocity, right?
Yeah.
Bike is just a constant velocity. And that was V0, we'll call it.
Okay. I've got the position went down.
All right.
I'm pretty sure that this one, the position of the car is a parabola, right? So it should look like this.
Hang on. You're right about a parabola, but this is saying that the car is actually starting at some big position and then moving backwards, coming down, and then going back up. So I think we need to define a better system here for everything position.
I guess that's why it's useful to always make sure that the stuff you're drawing makes physical sense.
So what you guys did also is when you draw a graph, you could pick different points and see if they actually correspond to the situation that you have. That's what Maria did, basically. She said, oh, this doesn't make sense because it did not start with this at this position, and picked up a few points and figured it out.
So if we have time and position. So what if we called this point, well, it is 0, but what if we called it the point that the car starts at?
That makes sense.
It starts at position 0 and then goes, because then we want a position related to distance after that the biker catches the car.
Yeah. Oh, so it'd be a parabola, but it'd only be the right half of the parabola, right? It'd be like that.
Yeah, that looks good. All right, and then the bike.
Now, how can you check? Now, again, you can pick different points in position. Where's the car when time is equal to 0?
So when the time is equal to 0, it's at position 0, which is just what we want.
And the other thing that you know is the velocity of the car when the position is equal to 0, which is
0.
So this means that
the slope should be 0.
Yes.
And it is indeed 0 here.
Yeah.
Awesome. For the bike, though, it starts behind the car, so we're actually going to need this axis here to
Oh no.
it starts position D behind it, right?
Yeah, but what
So-
slope should it have?
At time 0, hang on, -D. Well, it's traveling at a constant velocity, so the position is just going to be a straight upward sloping line.
Okay. How about that? Wait, it never hits the car. Shouldn't it be at the same position as the car if we wanted to?
Yeah.
So maybe it looks something like that then.
But so here, the bike and the car are at the same position twice. So I think that's the first.
How does that even happen though? How does it catch the car twice?
So at the first one, the bike is catching the car and goes past it. But the second time, the car, because it's accelerating, going faster and faster, it then catches the bike again.
I see. Okay.
But we want the bike just to catch the car.
So something like this. Something like that, where it just touches the line at one point.
Yes, so here we know that both position graphs are only going to meet once. It just catches the car. That makes.
Oh, but this is like a tangent line, right? It's only touching at one point, which means that not only is the position the same at that point, but at that point the velocity of the car and bike are the same.
That's right, and that makes sense from even just from the wording of the problem too, because if at that point the bike was going slower, then it wouldn't have caught up at all. It would have been the first line you do here. And if the bike was going faster than the car, it would have been this one, where it overtakes the car, then the car overtakes it again.
Right.
So they have to be the same velocity at the point in order to just meet like the constraints that the problem imposes.
All right. Well, I guess we can start writing down equations.
Awesome.
So this was a nice way of representing the two motions and the constraint that sort of connects the two motions together. Or we can think about it as boundary conditions. And here you figured out that there could actually be more than one situation depending on what the velocity of the bike is and what the acceleration of the car is, because you wouldn't know what that could be. What's given the problem is the relationship between the two motions. And this is what you can use to get the solution.
All right.
Excellent.
So now, in actually solving this, we'll probably only care about the velocity and the position, right?
Yeah.
Okay, so we had. So now we have our equations, but wait, can we take a step back really quick and do the SIM thing?
Sure.
Just so we know everything that's going on. So the system, we have two of them. We have a bike and a car, and that's what Safe was talking about. We have different things that have two different motions, and our interactions. Well, there's no forces, but we have sort of the interaction is the motion.
They have two different speeds.
Yeah.
So whenever we talk about kinematics, interactions are always hidden because we don't explicitly talk about interactions. We can figure out interactions by thinking about the motion. So if the car is moving with a constant acceleration, what does that tell you about the interactions? If something is moving with a constant acceleration, does it mean that there's a force?
Yes.
Yeah.
So there has to be some interaction with something else that produces a force, and this force has to be constant, except that this is not really that important in the problem. You know that it's there.
Right.
And that's why you have a constant acceleration, but you infer that from the motion, not from the forces. They don't mention anything about the forces.
So do we just write something like
zero force and a constant force? So the bike must have zero net force on it.
Force on the bike, okay, and then
Or zero, no net interactions. And the car must have a constant
force on it. Okay. And then modeling, we just said kinematics.
Yeah, but you can be more specific because the bike has a different model from the car.
Oh, true.
Well, you can think about it as a submodel because the bike has constant velocity, right?
Mm-hmm.
But the car has constant acceleration.
Right. So our graphs are kind of the model in this situation.
Yeah.
Awesome.
And again, you can represent that a different way, which is the equations, and that's what you guys are going to do now.
Yeah.
Okay. We can get our equations right from our graphs, right?
Yeah.
So this is velocity. So we have v of the bike just equals v naught. And the v of the car from kinematics is going to equal v naught plus acceleration times time. Although it starts from rest. So this goes away.
Okay.
And so for the x ones, we're saying that's the big formula, but can we eliminate any of these terms?
So the bike started at negative d.
So this is negative d.
And acceleration is 0 because it's moving at a constant velocity.
Righto. And then, of course, it's moving at a constant velocity over time, so we like that term. So we just have negative d plus v naught t.
Awesome. And the car.
Got that down.
Great.
But we said it starts from rest, and we defined its starting position to be 0.
So we can get rid of the first two terms.
And we know that these things have to be equal.
And we know that these things have to be equal.
Awesome.
So let's set them equal.
Yeah.
V naught is equal to AT, and negative d plus V naught t equals 1/2 AT squared. You know, Maria, I'm seeing that we could do some plugins here.
Ooh, I like this.
I think that we should take the fact that AT equals V naught, and we should take the AT and put it into the V naught here.
That looks like it's going to be nice, actually. So we have...
I'm seeing a collection of terms here.
Yeah. Subtract this, and then move this to the other side. And then we have d equals 1/2 AT squared. Awesome, but then we still have like
this
a
doesn't
and
say anything.
t.
We need x of the car.
Oh, wait
right?
a minute. This is the x.
Right. Back when,
car.
yeah, before you erased it, we had written down that x car is equal to 1/2 AT squared, and that's actually what we have right there.
And so we've just kind of arrived at our answer without even realizing it, in a way. Is there another way that we could have done this?
Well, it seems almost like cheating. I mean, this is one of the problems that there is a trick to solve the problem very easily, because you guys did not do too much algebra. But there has to be a way to actually properly solve it. The tricky thing in this problem is that you have no idea what acceleration is or the velocity, but somehow you manage to eliminate both of them and to apply the constraints that you have. The other way that you can think about it is that you can try to solve the general equation, because you said, let's assume that you have no idea what the acceleration is or the velocity. What you would do is you do the same thing that you did with that, oh, okay, so what if I change the velocity of the bike? The velocity of the bike could be too low so that they will never intersect, but it could be too high so that they will actually intersect. The two graphs will intersect twice.
And so we're looking for something basically with one solution.
Yes, but one solution of a quadratic equation.
Yeah. Oh, that's what we have right here.
You've already eliminated V naught, but if you kept V naught in, then you'll have a quadratic equation in terms of in time, but you have two variables. You have A and V naught. And basically, you want this combination of A and V naught that will only give you one solution. So if you write the general solution for this quadratic equation, and look where you only have one solution, this basically will give you the condition of V naught and A that will give you one solution.
Gotcha.
So can we look at that real quick? We have...
So you might want to write actually your quadratic equation, because I don't see it anywhere, so you might want to...
So that's just this guy.
Yeah.
So we have 1/2 AT squared minus V naught t plus d equals 0.
Yeah, and then you're looking when the square root of b squared minus 4ac is equal to 0, right?
Yeah.
So you can plug in for your ABC and then look when you only get one solution for the quadratic equation.
So we would set this part here equal to 0.
Yeah.
Okay.
So this will give you a lot of algebra and might be a little bit messy, but this actually should give you the same solution. Do you guys want to do it, or should we just move on to the next problem?
Not the biggest fan of algebra. Let's move on to the next problem.
So this is something that we always stress in class, that, what's important to actually figure out the physics. And in the written exam, this is what we care about.